Okay. So here in this session, I'll just try to provide you an overview of where we are and how the future works. But before that, I just want to say, just like Dan indicated, it has been a pleasure, Dan, working with you for 13, 14 years, coming up with all these machines. And we have an informal deal with Dan. Once he retires, I'll retire. Okay. But he doesn't know when he will retire, so I don't know when I will retire. Okay. So we'll try to continuously build machines for the next whatever X number of years. Okay. As you know, like we have just a very high level perspective. I mean, go back like almost 50 years. We started with scientific computing, the big data came, then we are in the exciting AI world. So what is happening? I mean, how every one of you also see on these machines, users are trying to bring not just their HPC need, they have AI need, they have the big data need, but below, if you see the hardware, it remains the same. Okay, so we need the scale up, we need the scale out, we need scale across. You name anything, any of these upper level stacks can need it. So what we have been working, even though MVAPICH project started with the HPC focus, the same layers can be reused because in the end it comes to the communication. So can we really have an MPI-driven middleware to actually enable all these things? And that has been our recent goals in the last several years. I'll try to show you the things. So this will be the kind of the outline. I'll start with a brief overview of the MVAPICH project. And then many years, I think it has been what, 4 or 5 years, we changed to this MVAPICH Plus. I'll give you a broad idea there. Then I'll try to show you some of the very latest release. I think Dan indicated that we have the 501 beta on the NVL72. I'll show you some very latest number. Then the new HPC AI stack I introduced, OSU micro benchmarks, and then some of the upcoming features. So as many of you know, so we started this project in 2000. And when the InfiniBand just came, that time Mellanox, I think Rich is sitting here from Mellanox. We started working with them for 14 years with Mellanox. When bringing all these IB, RDMA, there was no software stack. So MVAPICH, we were in the very right time to jump in. I'm very proud of my team. So we've been working here for 25 years to make this available. Of course, we started with InfiniBand, but now we have gone into all the different, you name any of the high performance interconnects, we have this. And as of now, like we have more than 3,500 registered organizations in 94 countries who use our stack. A lot of people don't register. They use all the Gmail, Hotmail and all, but these are the valid email addresses, organizations. And more importantly, earlier this year, we crossed 2 million downloads just from our site. Okay. Of course, it's a part of all other stacks, SPAC, OpenHPC, vendor stacks. We can't keep track of this. We can only keep track of our things. And of course, we have been in this field for 20 plus years, helping with the community to build systems. And just like with Dan, we take it to the really next level kind of thing. Here you can see the kind of the download counts steadily increasing. But this is the heart of the system. We started with like a support for all the different networking technology, all the different CPUs, GPUs, DPUs, etc. But this is where our innovations lies. Like how do you really design the runtime for the scalable communication? We started with MPI over the 15 years back. PGAS became very important. Hybrid MPI plus X became important. So we tried to support. In fact, some of these things are again coming back. Okay. But recently, not only like we have HPC, but we have the AI and also the big data science. I'll talk a little bit later. So it's the same stack. You can actually use it for all your the need. So just to give you, like, I think yesterday somebody was talking to me. We actually, even though it is from academia, we spend real effort. The software engineers and a lot of students, we run every test, like it says almost like 1,800 core hours per commit. Okay, so we make sure whenever we make a release, it is actually working. So there is a functional part, then there is a tuning part, testing, optimization, that also we do. So when you download our stack, and you are guaranteed to actually it will be running and delivering very good performance compared to the other stacks. So it has been very hard, but again, I'm very proud of the teams, the students who have come over the years and have contributed to this. So what we, earlier, if you remember, I go back like a circa 2002. So this is where in the beginning, it was verbs, okay, for the InfiniBand, and then the PSM was from the Q logic. So that's how we had all these designs. Then we extended, of course, to iVerb, Omnipath. So that version MVAPICH was running for some time. Then, of course, the MPI 2 came, MPI 3 came. So we moved to something called MVAPICH 2. And this was the time when very quickly all this GPU came. So we worked with Mellanox and NVIDIA. At that time, they were separate, coming up with this GPU direct RDMA, all those concepts. We worked together to bring how to bring MPI there. But then similarly, there was also AWS added this EFA. So we had very quickly, we wanted to provide solution because the community needed it, but then the code got bifurcated or trifurcated. Like we have different versions. Then if those of you remember, like attending MUG for many years, we got the feedback saying, I mean, it's becoming very difficult. So these things we are trying to phase out. And at the same time, what happened, so all these, we had MVAPICH to GDR, MVAPICH to X, MVAPICH to AWS. So we try to combine all this into something called an MVAPICH Plus. So we have a base version called MVAPICH, and then MVAPICH Plus, which has more features. But then what has happened over the years that the field is moving like HPC to the AI to the big data. So once we have designed this library, the question is, can we use the same communication layer? So we are not saying, okay, you try to, people have a misconception saying that, okay, we are saying AI workload, you need to write MPI. No, we are not saying that. You remain on the PyTorch. But when it comes below, we can use the MPI communication layer, okay? And that's what you will see some numbers so that we can deliver you the same, like it's just like, think of a car engine. Once you have a built new engine, you can have external things saying this is the Model X, this is the Model Y, Model G for different users. Okay, that's what we are trying to do. And that actually provides very good scaling, performance portability, and the more important is the vendor neutrality. These days, if you see like at least 3 CPU types, x86 AMD, x86 Intel, and then the ARM, 4 interconnects, IB, Rocky, Slingshot, Omnipath, Express, that families. And I've listed GPUs 3, but might be 2, the NVIDIA and AMD. So if you do a math, there are like 36 combinations here, okay? So which stack? I mean, vendor can give you 1 CPU, 1 GPU interconnect. But the user community, if you are an end user, you want to have the full flexibility. And that's what we are trying to provide. You will see whatever designs we bring, it's not only for HPC, but for AI, also for the big data. And that's what we are trying to provide, and both on-premise and cloud. So then what happened? So this is what happened. If you, some of you are the old timers here, if you remember, we had the Open Fabric stack, where both IB and iWork were coming together, but then that got fragmented. And then the community went in UCX way and OFI way. So then very quickly, we found the need that, okay, we have to provide support for both of these. So we redesigned, so that's what happened from the 3 series. We supported UCX and OFI, but through that, we lost our freedom. Earlier, we were designing at the verse layer and the PSM layer, which was the very lowest layer, so we had a lot of control. So now if we go through the UCX and OFI, we lost that control. But we quickly enabled so that people can start using it. And now what is happening is we are trying to bring back all our old designs, okay, because we had all those full control at the verse and PSM. So now with this new UCX and OFI, we are trying to bring our designs back so that they can coexist. And Dan indicated to this in his talk. I'll show you. It's really complex these days. I mean, if you think of like an NVL72 with NVLink, IB with a UCX, MPI itself has around 200 parameters. UCX adds another 100 parameters. How do you make sure that these are all working together to give you the best performance? And the biggest thing is to run all these things, to understand, you need dedicated access to the system. And that is becoming a challenging, just like you were saying, there's so much demand. And I'll show you like we got, thanks to Dan and his staff, we got some dedicated access to the NVL72, just as 18 nodes. We got 60 node access over a period of time, 3 weeks, but not for the entire system. 1 node, 2 nodes, and sometimes we got what, 2, like an 8-hour slot and a 5-hour slot for the entire machine, and we are able to optimize. I'll show you the numbers, okay? And thanks to all of many students here who worked in the middle of the night, we get allocation, they remain awake and do all these things. But But that is becoming very complex. So that is, think of just 18 nodes. Now Horizon, I mean, think of like a 3,000 GPUs and all. Just to tune, it is not just us. Any layer, anybody else has to have that kind of time and effort to optimize. Okay, otherwise you will not get the results. So now it's much more easier. Like we are trying to conform to the standard. Like if you have a 3.x MVAPICH plus, that is MPI 3 standard. 4.x is the MPI 4 and MPI 5 standard. So now let's see some of these, the very latest. So this is our MVAPICH plus 5.0, and then we had a minor release 5.01. These are the standard GA release. And this is what I indicated through both OFI and UCX, you can build. And depending on which network is exposing to which layer, you can actually get all these combination, as I said, CPU, GPU interconnect combination. And so think of this is like a base module. Now on top of that, I can have add-ons. Okay, and this is where we are having MPI DL, MPI QMLs, MPI Spark, the new HPC AI stack. So think of there is a base runtime, which is already giving you the best performance, and you can bring the other upper layers on top of those to enable to the end users. So I'll just try to show some sample numbers here, just to show you that vendor neutrality, how we are doing. So we have Vista from TAC, of course, it is a Grace Hopper CPU, NVIDIA, the Grace Hopper, the NVIDIA GPU with InfiniBand. Think of Stampede 3 at TAC, it is an Intel CPU, Intel GPU Omnipath. Cosmos at HDSC, this is the MI100 300 APU plus Slingshot. The Frontier at Oak Ridge is AMD CPU, AMD GPU Slingshot. So when you make a release, we actually support all this combination, and that too also the best performance compared with the vendor proprietary library. Okay, so I'll just show you some sample numbers. Again, the slides will be posted, so you can take a look. So this is like a, on the TAC Vista, on the Grace ARM CPU, already use is getting very important these days, both for HPC as well as AI. So you can see, compared to OpenMPI, we're able to deliver like a 61%, 86%, 72% benefit. This is on more number of GPUs, like a 256 GPUs. We're also comparing with Nickel, the system Nickel, as well as the very latest number when it was taken, it was 221.5. So you can see this is like the MVAPICH plus, short, small message, medium message, large messages, we are able to do equal or better than even the Nickel, which is a vendor provider library or even OpenMPI. This is some application. This is like a WRF. And here you can see OpenMPI versus MVAPICH plus. This is running on like a 1152 cores. We are able to give like a 32% benefits. This is the TAC Stampede 3. It is actually Intel plus Omnipath. Okay, so that is where also we are able to run this in open form. The Scotch motorbike example on 1792 cores, we are able to give you 27%. Okay? And these are the public released. You can just download and run. You'll see this kind of benefits. Now the MI300A, we have a very active research going on, and we have started pushing the things. MI300A, as you know, is the APU architecture. This is a very new architecture where both CPUs and GPUs can share the same memory. So that opens up a lot of optimizations at the MPI layer. So here, if you see, this is on the SDSC Cosmos. Tomorrow, I think we'll have a talk from Haider. He may go into more details. So this is a Cray system. So the Cray MPACH is the standard vendor proprietary library. But compared to that, you can see this is actually the older release. We are able to give you like a big improvement for all the collectives here GPU. Now the Frontier, as you know, it used to be the #1 system earlier, and now it is what, fourth, I believe. So that is also a Cray machine. Now, what is happening, again, no offense to vendors. Vendors are always putting a condition saying that only their library will be supported. Okay, that is no problem. But then the end users want the best MPI library. Okay, so what Oak Ridge people have done, they have allowed something called a user supported module. Okay, so they have opened it up so that we actually put our version there and users can use. And then if they have any issue, they get back to us. Okay, so that is the Oak Ridge model they have come up with, and I'm just sharing that so that if other centers would like to do that, we'll be very happy to work with you so that the end users actually get the best benefit. And so there I'll try to show you the very similar things. This is on the already used Frontier. This is the AMD GPU, so that's why they have this Nickel, which is the equivalent of like the Nickel from AMD. The same story holds good. If you see the black line, we are able to perform equal or better compared to the, here it is a MVAPICH or the system record. So those are the kind of the very sample numbers. We have a lot of numbers we have published at different places. You can take a look. But this is the very latest 510B. We just released last Friday. We always try to do a release before the month. But this is where you will see, I was telling, like, let's say this is an IB system, especially we try to do it for the NVL 72 rack at TAC. So it already has UCX, but then we had our own shared memory, okay? So the question is, okay, how do you choose? Do you choose always go for UCX shared memory, or we have our old shared memory design? So this is the kind of the new hybrid designs we are trying to bring in. And then I'll go into more details. So we also provided a lot of optimization for the bcast, and this is also new. You know, many people are heading into the B float 16. Okay, so then the MPI layer also has to provide that. So that's what we have done with this latest release, and I'll try to show you some numbers. So these are very fresh numbers, as Dan said. In fact, I sent him the slides Sunday morning. We are working to get all these numbers. So look at this is a tax system. Like, think of a rack, and NVL 72 rack. There are 18 nodes, but I think 16 nodes. That's how we run things. So 64 GPUs. So if you take like a bcast compared to the OpenMPI, which is installed here, we can see you like for very large and all, we can give you 6.13x benefits at 4 megabyte. And this is that combination of all the UCX and MPI parameters we have actually worked, like which work together to give you the best. And we have actually delivered a code with a module file so that end users don't have to worry about that. So it is installed there with all the parameters, so they see this kind of benefit. Same thing here, GPU already use, very similar. Like this side is the small messages, large messages. Here you can see we get a very big benefit, and this is to the very latest Nickel 237 one, which is the very latest. CPU already use. That is also becoming very important these days. If you are running, like Dan was telling, a lot of people want to run even on the CPUs because GPUs are very expensive. So we are trying to do both the CPU optimization as well as GPU optimization. And this one, I think the HPL, I think Ben showed these numbers. Really, we really went through the HPL trying to understand what is happening, and we optimized. So here, if you see like a 32 GPUs, 64 GPUs. So we are comparing different, like a binding mapping, because OpenMPI didn't work actually, and some of the mapping, it was crashing. So we tried here, and you may see, like, let's say this is the MVAPICH number, higher it is better. So we are almost like reaching closer to the Rmax. Okay, the benefit is 1.47%, but those of you who are familiar with HPL, that itself is a big. If you put 1%, 2%, you get so many higher ranking in your top 500 list. Okay, so that's what we are able to do, just using not just like the lower layer, but taking a combination of usage parameter, MPI parameter, application, and trying to see for this application what exactly, how you get the best performance. So I'm just trying to give this example so that if there is a need, if any HPC centers, and then you have some killer applications, we'll be very happy to work with you. It takes time. It takes time and it takes effort. It just doesn't come magically, but we can work with you and to deliver the best performance for that application on that system. Okay. So then this is the new HPC AI stack. I think we introduced that yesterday. So what we are trying to do, think of like these are like the MVAPICH plus whatever I showed. It delivers the best performance here, compute, CPU, GPU, storage, internode, intranode, across anything you can think of. We have optimized that. So think of that as just a runtime. Okay. Now, once it is there, now what we have done, like we have actually put a PyTorch interface to that. Okay. And in fact, a few years back, we contributed several patches to PyTorch community, and they didn't take it. That's okay. What we did is we did a fork, and then this is the version out there. So you can actually download from our site and install it on yourself. Okay. And then on top of that, earlier we were only focusing on training, but now you can see the training, Torch Titan, Megatron, VLLM, ST-Lang. On top of that, then the entire ecosystem is there. Once you optimize it, then you can just run it on your all your AI workload. So that is the direction we are trying to push. So in fact, even though PyTorch community didn't accept our patch, there is a new PyTorch conference which is taking place in October. So we had submitted a poster. So they just accepted yesterday night. So we'll be presenting this stack. I don't know whether it's good or bad. We'll see how that community reacts. But that's what we're like trying to really put end users get the best performance. And just like Dan said, if a machine costs 200K, I mean, you really want to get out the best performance there. Otherwise, you are wasting your money, okay? Whether it is your HPC or AI or any of the data needs. So what we have done here is the HPC AI version 1.0 release. Just like MVAPICH, you can go here. And let me show you some of the numbers. So this is actually distributed data parallel training on Vista. It is the earlier release, MVAPICH 4.1. So as you can see, this was that time, it was Nickel 2.293. And this is like a 1 GPU per node, so over like a 64 GPUs, as you can see, with small number of GPUs, you don't see much difference. But as the 32, 64 GPUs, you see the time our new stack is able to deliver you better performance in the training. Okay, and this is all the training details are here, and this is like running with PyTorch 2.10. Same thing, this is the very new, I think, Shoaib, thanks to Shoaib, he just sent me this number just 30 minutes back. This is the bfloat 16, because we enabled in our 5.1 beta, whatever we implemented. So that bfloat 16 is actually now implemented in MPI and also implemented in the kernel level collectives for the GPU. Okay? And now you can see the same trend. So here, if you see 16, 32, 64 GPUs, the time per iteration, we are able to give you almost 28% speed up. This is on the frontier on the MI250X, very similar story. So this is again like a GPT-2 DDP, 1.5 million token per iteration. And here we are comparing with the Rickle, because that is the AMD system, AMD GPUs, very similar things you can see here. As the system size is increasing, we are able to give you good performance. Now, again, these are some sample numbers. And also, as you know, the OISU micro benchmarks, that project we also started, I think around 2003, because that time people knew how to measure the application level performance, but nobody knew how to measure MPI level performance. That's why we call it like an MPI micro benchmark. So how much like a send receive takes, how much all reduce takes. So that's how we started. So over the years, that project itself is going very strong. The latest GA version is 7.52. But we made a newer series has come, 8.0 RC. If you have not used that, please use. And we are restructuring the library to make it much more easier. So instead of running like we have reduced file, less duplicated code, and enhanced runtimes to facilitate. Similar to IMB, if some of you have run IMB earlier, you can run in the same manner and it remains backward compatible. So we are strongly encouraging the community to move to the 8.0 series. Okay, so that it will be much more easier for people to run this. Now, of course, for the last few years, we have received some requests to make this OMB open, totally open. The way I mentioned, like it is an open source code, but it's still within the OISU system. So we are gradually trying to see on the Now Lab, GitHub, whether we can make a public repository so that people can actually start pushing patches themselves. Of course, you have to provide a maintainer and all those things that are additional overhead, but we are thinking of this. So let me go into a little bit more, what are these upcoming features? So this is what I indicated, like a APU optimizations, some GPU-aware hierarchical collectives. This is DMA accelerated framework. This is something new. Most of the time in the earlier MPI, you use the DMAs of the NICs. But if you take any look at the onboard servers, they have also DMAs. And those are mostly sitting idle these days. So how I can combine the DMAs from both sides, the NIC DMA as well as the onboard DMAs, and to boost the performance. So then, of course, I talked about this AI for MPI. I'll try to show you something. And the final thing is this, I think it was brought up yesterday, GPU-initiated communication. Okay, so how we can take advantage of this very latest thing. There are multiple terminologies. Yesterday we saw from the D-Matrix talk, and how we can take advantage of that, I'll try to show. So again, these are some dense slides, but I just want to highlight a few things. So this is what we presented in the IPDPS this year. So the APUs, if you think of like the same memory is given to CPU and GPU, I can actually combine the power of both. So think of like there is a GPU is doing all reduce. Most of the time, the CPUs are sitting idle that time. So can I do some work distribution? So that means the same all reduce, small portion of that the CPUs will be doing in parallel to the GPUs. Okay, so we call it like a collective onloading. Okay, we are taking the QLogic onloading term, now re-bringing it with AMD APUs. So I can accelerate. The same thing also I can do. If a code is running on the CPUs and you have GPUs available, I can offload those to GPUs, not the computation. We are purely focusing on communication. So based on the system, how the job has been allocated, we can do both onloading or offloading, and they can work together to boost performance. Okay, so this is our new series of designs. I think there's a poster here also. Gautam is sitting here, right? So he's the main student driving this. So here, if you see, here we are showing up to 76% improvement for all-to-all, and compared to Cray MVAPICH, up to 66 improvement. So some of these are already there in the code. You can try, and gradually we are moving more. So this is like on the STSA Cosmos. That is the MI300A architecture. The same thing, if you see here, like this is the very latest release with the proposed. We are able to give you like a 27%, 20%, 31% benefit. Now with all these GPUs, again, like Dan indicated, with NVLink coming, IB coming, there are more parallelism in the network. So how do you really take advantage of that? And also, most of the time, there is these systems have, like, let's say I have 4 GPUs or 8 GPUs per node. So you can do some intra-node optimization, then inter-node optimization. Most of the time, people do it in 2 steps. Either I do intra-node or inter-node. But you think of like, hey, I can do parallel pipeline. Okay. While I'm trying to do some intra-node, I can also do inter-node or the vice versa. So we are exploring all those algorithms, and this was a paper. Tomorrow we'll see it in a short talk, and very similar kind of things compared to Cray MVAPICH. You can get like a 1.23x or 1.x faster. Now this is the DMA I was telling, using both onboard DMA as well as the NIC DMA. So here you can see like let's say 3D stencil application, different problem sizes. We can give you like a 27%, 18% benefit kind of thing. So this one has not gone in. We have papers we presented at ISC this year, and this will come up in the next few months. So this is for the AI for MPI, as I was telling, not MPI for AI. There are so many parameters here. Can I actually use a lot of collectives performance, take that data to build an AI model? So then there is a new system comes up, like just like Dan is deploying Horizon. We don't need access. No, we need access. Okay, I'll not say we don't need access. We can run some few experiments and use that together with our AI model for an inference. Okay, and now you'll say, okay, if I want to do vcast, instead of running exhaustively with all combination, we can actually come up saying, okay, these are the algorithms which will be good for the Horizon system. So there is a new project we started. This is an NSA-funded project. So saying AI for MPI, but you can take the same ideas for other stacks also. So we presented this at a AI for CIS HPDC workshop. But of course, this has not gone yet into the release. Gradually, we are trying to improve on that. Now, this is the very latest one, the GPU-initiated communication. So those who are not familiar, I mean, the GPU direct RDMA, when it started saying, okay, if my GPU is sitting next to the InfiniBand, I can move the data. But most of the GPU related things, still CPU is doing the control. Now, of course, the idea is that, okay, can CPU be totally eliminated? Okay, so that means your entire thing is running in the GPU. So this is a very initial work. So what we have done, so this is like, I think of, this is an internode latency. The entire thing is running in the GPU, okay? Of course, you need to make sure that because GPU is a kernel-oriented thing, there is an additional launch overhead, there are sequential code. So all those things you need to be aware. So there might be higher latency. However, overlap, look at the overlap, okay? So it's almost like 100%. I can actually convert a stencil code to a totally GPU kernel, including computation and communication, and just give it first to the GPUs, and that's all. Then the CPUs will be totally independent. Okay, so I can get that kind of, even though my communication may get slowed down, but my overall execution, when I'm trying to take a look at overlap of computation and communication, we may get very good performance. And that is the direction where we are going. And I think even a lot of other people like Dematrix and all also are exploring these, even for AI inference and training kind of thing. So that is the focus, which we'll be doing very soon. You will see another 6 to 9 months. You'll have some of these releases coming up. So then let me quickly move forward. So as we are enhancing the MVAPICH stack, and then the HPC AI stack takes advantage of that, we are also updating the HPC AI itself, not the MPI part, the upper parts. Okay. So we have two designs here, MAC attention and the Nimble design. So this one is, we presented at MLC's conference this year. So it is basically, think of with all these long inferences, there is a big focus on long context decoding. Okay. So you want to make this context very long. And here we have actually in this paper, we call it like a MAC attention with a very good saving in the KV-CAS accessing. We're trying to make the performance of all the inferences much more faster. And that is the kind of the design we'll try to put it at the upper layer of the HPCI, not the runtime, but for the inference. That is one work is coming. So this is another work, which was presented at the IPDPS 2026. So here it is called like a Nimble. So the idea is that even at a high level, I'll not go into details. I think, where is Jingan? I think he will be here. He will give a short talk. There is also a poster. So even like most of the time, if you go to the nickel code, I know Rich Graham is sitting here. And so let's say I try to find the best path. I have a combination of GPUs. Then I come up with a topology and I say, okay, this is how you should do. But you can think of some GPUs are also sitting idle there, if you really take a pattern. So the question is, can I take help from some other GPU? Like a GPU 1 is talking to GPU 5, GPU 2 and 3 are sitting idle. Can I reroute through that? Okay, so that is the kind of the very, the principle there, so that I'm trying to keep the GPUs busy. Just like I indicated earlier, offloading, onloading between CPU and GPU, now I can say the GPUs are themselves working together in a collaborative manner, so that will be there. So these are the kind of some high level things, whatever is coming up. So let me conclude here. So as you can see, like we have been, MVAPICH project has been going steady for the last 25 years. We are providing not only the MPI solutions, but also this new HPC AI stack. I didn't cover here the big data stacks. I think the interest has gone down, but we have all those solutions also, like a Hadoop running over MVAPICH, the SDFS, all those things running over the same MPI runtime. So people, depending on the interest in the community, again, we may try to bring back some of those things as needed. And so several people here sitting, they did all the work. Jitin did all the very beginning Hadoop work. Professor Jiawil Lu, who is sitting there. He was there as a postdoc and research scientist. So all of them had done those kind of designs, and those are also available outside. Yeah. So I'd like to thank all the sponsors here for our work over the 25 years. A lot of people have provided in terms of equipment, funding, otherwise their help would not have done. But last but not the least, these are all my heroes. Okay. I think they have over the 25 years, they have actually come, done the great work, and have left and still doing great work in the community. And we every talk we present, we acknowledge all our team members for the last 25 years. So with this, I'd like to also indicate this. I think Navaras indicated this. We give a lot of tutorials. Yesterday, you saw some small glimpse of the MVAPICH tutorial and the HPCI tutorial. So we have both this tutorial accepted at the Hot Interconnect 2026. This will be on Friday this week. We'll have this presentation. We have the full day versions accepted for SC 2026. So if you know any of your colleagues or anybody would like to attend all these tutorials, please feel free to them to join. This time, actually, we are going, in fact, to even to the South America. There is a conference called Carla 2026. So we have both these tutorials accepted there also. So we'll have a version. So if people, so we are getting a lot of invitation from all these different conferences from all over the world, so that we can take actually all our expertise and share with people worldwide. So with this, let me stop here and I can answer very few questions now. And then, of course, I mean, if you have any other questions, I'll be very happy to answer later on. Thank you. Any questions from local here or online? Go ahead, Dan. Yeah.
Push and hold it? Yeah.
Yeah.
Okay. So AI inference training, multi-trillion dollar problem at this point. But how much uptake are you seeing from either the vendor or like the inference companies, deploying LLMs and actually optimizing? It seems like they'd rather just throw money at the problem than squeeze a few more % out of the hardware they have. I mean, are you seeing a lot of interest in consuming this stuff in the AI space?
Yes and no. So what is happening? Sometimes you mention all these, like the big players, they don't care about our solution, okay? Because they have all in-house expertise. They have 100 people working on this and that. But when it comes to let's say within OSU, okay? I'm just giving examples. Like we have a new, like AI institute going on. We are setting up an AIX hub. All these user scientists, they are also using the OSC system, but they are hungry for performance, okay? So this is where we are trying to enable the community. Of course, if you're using the OpenAI, yeah, go for their solution, okay? And no offense. So we are trying to have a grassroots level analysis, and hopefully once these people see the benefit of this stack, saying they are getting benefits of 15%, 20%, then might be some of this, the other vendors will start looking at. So that is the approach we are taking. But again, the solution is public, anybody can use it. It depends on the companies, their approach and all. I mean, say, once I talked to a company, I mean, they said, no, I know you are showing 15% benefit, but we have invested so much money on our stack, we don't want to change it. That's okay. Any other questions? Any other questions from online? People can unmute and ask questions or post it in the chat. No? Okay, go ahead. Yeah.
Yeah, so I had a quick question. So I saw some inferencing data, I think there. So are you integrating with like VLLM and SGLang?
Yeah,
that's the core. Okay, that's the core.
Yeah.
So is there any hope of us getting to an MPI solution instead of a completely fragmented CCL solution?
Yeah, so let me go back to this slide. I think what I'll try to. So what we are trying to do, so let's say this stack, okay? So there are two parts to it, okay? So one is, of course, the MVAPICH runtime. So here we can see, like, we can optimize all the collectives, whatever is needed. But we have started also working the upper parts. So that's what I indicated, like we have an enhancement with VLLM or SGLang and all. So those are against the existing modules, because there is a VLLM community, there is a PyTorch community. So we are working at both the layers. We are working at the runtime, which is the MPI things. We are also working at this PyTorch. I said they didn't take our patches, but here you can see actually the PyTorch. If those of you are familiar, like a typical NVIDIA GPUs, they take it through the nickel. AMD GPUs, they take it through nickel. What we are trying to provide a conduit to go through MPI. So you don't make your upper level. We are not telling, okay, now you rerun your agentic frameworks using MPI. You are not telling that. You use your PyTorch, VLLM, SLang, whatever you remain, but the underlying runtime, we can give you the best performance.
So why did they take your patches?
It is a more business decision. People, that's what I said. They have again accepted the paper. We'll go there and then talk. Okay. So there is a lot of, this field is moving, just like Dan said. I mean, there are so many business deals take place and all that, again, there are pluses and minuses there. We are from like an academia perspective, we are trying to make those solutions available to the community, and those who would like to take it, they can take it. Those who don't want to take it, that's perfectly fine. Okay. I hope that answers. So this is the newer model in which we are working on. Yes, Abid.
So from the from the last few years, we have seen PMix is not doing well, and there are lots of performance issues. Not the performance; it's just the startup issues.
Yes.
PMix. So just like MPitch, are you also going backward and trying to use the PMI 1 or 2 rather?
Yeah, might be Nat there can comment on, if Nat you are there, the PMIX support. So that's again, it's a job startup issues, as you indicated. I mean, that itself is also going through many variations. So we are trying to provide kind of different levels of support. Might be Nat, you want to jump in? Yeah.
So what was the specific question on the PMI support?
So I was asking if just like MPitch, you are also going backward with the simpler PMI 1 or PMI 2 implementations.
Yes, I mean, we mostly are going to use those because most of the additional features for PMIX don't have, we're not seeing anyone that's really using those features. So if there's a specific demand for particular PMIX features, we can look at them. But right now, what we've seen is for the most part that the way people are using PMIX for MPI jobs is basically just using the PMI 1 or PMI 2 functionality, just starting a job and going. We're not seeing any real integration with the advanced features that PMIX is offering. So it hasn't really benefited us to add any additional complexity on the MPI side.
Okay. So I think let's take a break. Might be it's 10:45. I know Rich Graham will be giving a talk. Let's delay it by another 5 minutes. Rich, is that okay? We have flexibility. We'll catch up during the lunch time. So might be 10:50. We'll start back. So let's have some coffee break and then get back here to listen to Rich. Okay. Thank you, guys.